So this is our today GFG POTD burning tree. In this question, we will be given a tree, given a root of the tree, and we will be given a target node. And we are given that for the fire to cross an edge, it takes 1 second. So we have to return the total time in which whole tree will get on fire. So let's see the code. So as we can see, this is the main function. In this function, we have first created our adjacency list, and we have got the number of nodes in the tree using this much function. Let's dive into how this function is calculating the total number of nodes. This is the function find number of nodes in the platform. So here is the function. In this function, basically, I am using my in-order traversal using iterative method. Because in iterative method, we have control over the flow. So we can increment the answer, that is the total number of nodes, each time we delete a node. So this is the simple structure of in-order traversal. And as you can see, when there is a node that is deleted, then I am incrementing my answer, and finally I am returning my answer. That's how the total number of nodes is calculated. Now I am also calculated the parent array. That will be useful for calculating the path from target node to the root node in OON time. That is basically the node between the root and the target node. So initially I filled all the parent array with -1. You can also fill only the root with the -1, because for all the other nodes we will finally have a parent in our function call. So let's dive into how we are calculating our parent. Let's first consider we are building our adjacency list. So in this code, we will be building our adjacency list. So simply as we have calculated the number of nodes, so we can create that number of arrays. Here we have done the same thing. Now I am using a BFS. So which at each level, when I will be adding the next level child in my queue, at the same time I will also add those childs in my adjacency list. So that's how I am creating my adjacency list. This is a unique way. Normally we are not doing this in the graph function, but here we are doing because we are given in a recursive method. Okay, so let's see how we are doing this. We are simply using a BFS like how we do in the queue, how we do in the level of the traversal. This is basically a level of the traversal. So as you can see, if the deleted node left exists, then we are offering that to my queue, and we are also adding to my adjacency list, and also we are also adding that to my parent. So the next level child will have me as its parent. That's the main logic. So in this part, we are calculating the target to root path. As I've told you also before, that we will be using our parent array for the same. So initially our pointer is initialized to target, and I am using map for what? I am using map. Let me clear that. I am using map for storing value to IDX. Means what node value is present at what IDX. I have assigned each value to IDX because they can be like one node with a value of 1 and one node with a value of 1e5. So in that case, we are using only two spaces in the adjacency list. That's how map will optimize our code. So initially my PTR is at target. Now, what does it mean by PTR is not equal to minus 1? PTR will be equal to minus 1 when we will call the when we will reach the root, and after that we will reach its parent because the parent root is minus 1. So at that time this value will break. So we will first this is our target to root path. This is our list that will contain all the nodes from the target to root. So we are adding the PTR, and PTR is equal to parent array of PTR. That's how we are going. And finally we are reversing because let's say if the target was if the target was kitna if the target was 5 and our root was 3 and our target to root path is what? Let's say 5, then 2, then 1, and let's say then 3, because 3 will be our last node as this is our root. At this point we will break our loop. So what is more useful to us is the root to target path. So we will reverse it. And how will we reverse it? Using the collection framework collection dot reverse target root path. So the reverse path will be 3, 1, and then 2, and then 5, like this. We are also storing all the nodes between that path in our set so that we can search whether this node exists in our target to root path or not using O of one time. That is the main function to my. So simply I am storing my path nodes in my set. Here, there I have initialized, and here I have. Now I am calculating the depth for each and every node from the node. That means, for example, let's dive into test case. Let's say test case. Here I will be assigning it to a value of what is the depth? 1, 2, 3, 4. 4. For 3 it is 3, it is 2, it is 1, here for it is 0. 0, 0, it is 1, 0, and here 1. That's what the depth array will represent for us. So we have a filled depth array function that will calculate the depth for each and every node. So how is that filled depth array function? Here it is a recursive function. So its time complexity will be basically what? O n. That is the total number of nodes. Because we are traversing for each node only once. And once we have regulated the depth for that much node, then for that parent, we can only increment 1 to that depth and give the parent node that much depth. Here is the depth array function. If root dot left is not equal to null, so we are calling the field depth array for root dot left. If that's same for the right, like that. And here I am going from target to root. Let's say this for test case. For example, here in this case, our target node was 8 and our root was 1. So what was target root path? In this case, my target root path was from 8 to 1. That is in the reverse order: 1, then 2, then 5, and then 8, like that. And so what I will be doing? I will be first going to first number node. So I am at node 1. Now I will find the depth of this node. Depth of 1 is what? It is 1, 2, 3, 4. 1, 3, 6, 9, 10. So depth is basically 4. So what will be my answer? 1, 2, 5, 8. That is basically from the list I have gained 3, and from the depth I have gained 4. So answer is at now is equal to 7. Now I will go to 2. That is the next node in the path. I will go to 2. Then for that the depth is 1 because we are saying the other part of the depth that is not included in the target to root path. So our desired path will be 2 to 4. So depth in that part is basically 1. So there the depth is 1 and for the list we have to go from target to 2 basically 2 edges. So here answer will be basically what max of 3 comma 7 and that is equal to basically what 7. Similarly for I will do for 5 it is the list for it is the depth contribution is 1 and the list contribution is also 1. 5 to 8 is list contribution, factor is depth contribution. So 1 plus 1 is basically 2. 2 to 7 ka max is basically 7. And finally I will be going to 8. The depth is 1 and the list contribution is also the depth is 0 and the list contribution is also 0. So both contribution comes to 0. So my answer here will be max of 0 comma let me clear this to 5. So our answer will be max of 0 comma 8, 0 comma 7 and here answer will be 7. Yeah, that's how I am calculating the answer and finally I am returning the answer. Thanks, please like, share and subscribe.